We're back tonight for lecture number 5 in our Modern Marvels series, and we're going to go straight through now with no more breaks. Tonight we're going to hear from somebody who has had a lot of experience in designing and applying practical solutions to some of the problems we've been hearing about. Professor Robert Harris received an undergraduate degree in civil engineering, a master's degree from Caltech in environmental health engineering, and his PhD from Harvard in environmental sciences. He's a nationally recognized expert in the treatment and disposal of hazardous waste and on air, soil, and groundwater contamination. He served as co-director of the Hazardous Waste Research Program at Princeton University and as associate director of the Toxic Chemicals Program for the Environmental Defense Fund. He served on the Council on Environmental Quality appointed by President Carter. And he's using his expertise locally, you'll be happy to know, as a trustee of the Stony Brook Millstone Watershed Association. Co-founder of Environ International, Professor Harris is currently a visiting lecturer at Princeton School of Engineering. In that capacity, he's working with Princeton students on designing, applying green solutions to real local buildings. He tells me he's going to focus on practical applications tonight as he talks with us about putting the roof on greenhouse gas emissions. Bob.
Thank you. Thank you very much. Can everybody hear back there? Is it reasonably projecting? What I would like to do tonight, as Nancy suggested, is to talk about some practical solutions, but primarily associated with buildings, not just commercial buildings, but residential buildings as well. Most of what I will focus on, however, will be commercial buildings, and that's where my class has spent the last couple of years. We have participated in the design of a LEED building that Isles is building just on the border of Trenton and Hamilton for their use, for a school, for a job training center. And this past fall, we participated in the design of Bob Hilyar's new office building on Witherspoon Street. If you don't know, he is converting the old warehouse building for Jefferson Plumbing into his new offices. So we had a lot of fun thinking about how we might make that an energy efficient, a water efficient building, as we did for Isles. So what I'd like to do this evening is to try to answer these 3 questions. First, why should we build and or renovate buildings to be more energy and resource efficient? And I think probably all of you know the answer to that, but I'd like to answer it with my own spin. Secondly, what is the low-hanging fruit? That is, how can we do this in the most cost-efficient way? And by and large, in ways where the benefits will exceed the costs. And thirdly, how important is it to keep score? Now, why should we build and or renovate buildings to be more energy and resource efficient? I would submit that there are at least four very good reasons. First, national security. We all know that the world is running out of oil. There is international competition for oil resources. That we are vulnerable because we increasingly import oil, and therefore, as we learned during the 1970s, and most recently what happens when there is an oil shock or when there is unrest in the Middle East. Stability in the Middle East, I would submit, in part depends on our ability in the United States to wean ourselves off of oil onto renewable energy resources and fossil fuels within the United States. Some would say nuclear. I think I'm very skeptical that we can do nuclear power safely. We still don't have an adequate method for final disposal of high-level rad waste. Global warming, we know that man is contributing significantly in his industrial and other activities to the release of greenhouse gases, notably carbon dioxide, and that while there are other causes of global warming, humankind is contributing significantly to the acceleration of CO2 in the atmosphere and to rising temperatures and all that is associated with it globally. And then finally, and perhaps as importantly, I would submit that much of the efficiency that we can engineer into systems to make them more energy efficient, we can do so in a way where the benefits exceed the cost. And I believe that's particularly true with our buildings. So the answer is any one of these, I believe, justifies focusing on how we can make buildings more energy efficient. We simply are running out of oil. Globally, 40% of our energy still comes from petroleum. And the date when global oil production will peak looms in the near future. Global climate change is upon us, and we're still 80% dependent on carbon-emitting fossil fuels. And the global demand growth is accelerating, particularly in the developing countries, China and India. Since about the time of my birth, which was in the late 1950s, I'm sorry to say, we stopped being energy independent in this country. That is, we stopped producing as much energy as we utilize. And over time, production has lagged consumption. And of course, the difference are our imports. Now, we could say, what about ethanol? Well, ethanol will produce just a little bit, add a little bit to this curve, as will other sources, offshore sources of oil, sources in Alaska. What will make a significant difference is greater efficiency to bring the consumption curve down. That's where the great payoff is in narrowing this gap between production and consumption. If we go back just a second and notice that the rate at which consumption was increasing prior to the early 1970s was greater than it has been since. And indeed, if we measure energy consumption as energy consumed per dollar of gross domestic product, we see that the U.S. has improved efficiency since the early 1970s. Steady decline. That if this rate prior to the 1970s would have continued, we would be consuming twice as much energy today than we were back in the early 1970s. Today, we're consuming about 100 quads of energy, and if it were not for this improved efficiency within our economy, primarily in the industrial sector, but also elsewhere. If you remember how inefficient refrigerators used to be in the early 1970s, they're considerably more so now, as are almost all appliances. Let's just, for a second, think about where energy is used, what in the three sectors of our economy: buildings, industry, and transportation. Now, what I've done here is I've included here primary energy. In other words, buildings consume a lot of electricity. In fact, 70%, nearly 70% of all the electricity consumed in the United States is used in commercial and residential buildings. We know that it's inefficient to produce electricity, that for every 3 units of fuel, say coal, that we use to produce electricity, we get 1 unit of energy in the form of electricity. So if we account for this inefficiency, which is this part of the bar, we, in both buildings and in industry, in transportation, we use very little electricity in our transportation systems. We see that buildings, commercial and residential, consume nearly 40% of the energy consumed in the United States. And also about 40% of all the greenhouse gases are produced or emitted by use of energy in buildings, either directly or indirectly at power plants. Now, as I said, I want to focus on buildings, not only because it's the largest piece of the pie, so to speak, but also because I believe that there are enormous efficiencies there that are economically attractive to realize. Before I do, though, I don't want to stray too far from the transportation without saying that, of course, buildings and transportation are linked. Where we build buildings often determines the amount of energy we use in transportation. We build office buildings outside of metropolitan areas, and those who use that office building have to be transported to the suburbs, to those buildings. Then the overall energy that's used is greater than if those buildings were built more towards the center of gravity of the population using them. Petroleum has steadily increased. U.S. transportation energy uses 95% petroleum. And just to illustrate the important gains that we can realize through more efficient transportation, particularly more efficient vehicles, automobiles, trucks, SUVs, so forth. Just consider the production of oil in Iraq. And I carried it here. I did this a few years ago, up till 2004. And this is the production curve in Iraq. Looks like I'm losing my battery here. You can see the two shocks, the first Gulf War, the second invasion of Iraq, and how that influenced Iraq's production. What I would call attention to, and I think Iraq is second leading or third leading, right around the same as Iran, reserves in the world of oil. And the maximum amount of oil produced was about right here, almost 3 million barrels per day. That was the maximum daily production of oil in Iraq. Now, just for fun, I said, well, what if we increase our fuel efficiency of vehicles from about 29 miles per gallon to 45 miles per gallon, which I believe is technically feasible, or it certainly was back in 2004 and even more so today. That would save, that increase from 29 to 45 would save over 3 million barrels of oil a day. Just an indicator of how important fuel efficiency is in vehicles to conserving oil and energy in the United States. Oh, you have a better one. Ah, that'll burn a hole in the screen. Rob Socolow and Steve Pacala here at Princeton, as I'm sure you all know, published a paper in Science where he and they looked at the amount of reduction in carbon dioxide that would be necessary to stabilize CO2 levels in the atmosphere. And they suggested that this business as usual line, if nothing were done other than the normal increases in efficiency that we've realized, could be divided into a number of what they called wedges in order to stabilize the concentration of carbon dioxide, or the emissions of carbon dioxide, eventually leading to the stabilization in the atmosphere. Now, they did this for the simple reason of suggesting reasonably doable, achievable things that could be done worldwide in our economies that, when added together, in fact, could realize a stabilization in CO2 in the atmosphere. 4 of those wedges were energy efficiency, 4 were renewable energy wedges, 3 carbon capture, and so on. Stabilizing CO2, of course, means at what concentration? The current concentration of CO2 in the atmosphere is about 380 parts per million. Before the Industrial Revolution, it was about 280. And scientists will argue about what will prevent the catastrophic effects of global warming. And those vary from there shouldn't be any increase beyond 380 to 425, 450, 550. If I took a vote, I think most scientists would probably say if we can achieve 450, while there will be some negative effects, already has been, will continue to be, that's an achievable and a reasonable number to target. That would mean between 7 and 9 gigatons of carbon per year below this business as usual curve that I showed you. Gigaton is a billion tons. So avoiding 1 gigaton per year in 2050 requires energy use in buildings cut 20 to 25% below business as usual in 2050. So 20 to 25% energy efficiency in buildings. Now, that doesn't sound like very much, does it? And I don't think it is. And I'm going to show you why I believe that. Fuel economy of 2 billion cars, 60 miles per gallon instead of 30. That too doesn't sound like it's not achievable. Carbon capture and storage at power plants, nuclear plants, and wind turbines replacing coal power. Photovoltaic power plants replacing coal power plants, and so forth. But it's the buildings that I want to continue to focus on. And an illustration of the economies, the benefits associated with building green and with energy efficiency in our buildings. There's a study that was done by Capital E back in 2003 for the state of California. And what they did was survey about 60 LEED certified buildings. These were primarily office buildings. They were commercial. They were all commercial buildings. LEED is leadership in energy and environmental design. And it is a rating system that was developed by the U.S. Green Building Council, and it is one that I mentioned that Isles is using in its renovation of its building in Hamilton. What they discovered was that the cost premium, that is, in order to be green, in order to have a more efficient energy system, in order to have better materials that would result in fewer emissions of volatile organic compounds into the indoor air and so forth, it would cost somewhere between 1% and 2% of the capital cost of the building. And I have heard this number, 2% or less, or 1% or less, at just about every conference I've gone to, that it is only about 1% or so more expensive to build a LEED certified building than it is one that is a standard building. And that cost premium, considering the construction costs of those 60 buildings back prior to 2003, translated to about $4 a square foot of area of the building. The energy value, that is the present value of the time stream, 20 years of energy savings, was over $5 a square foot. So with just the energy savings, it would seem to justify the increased cost of building to LEED specifications. You'll notice way out here, this big bar here, productivity and health value, that is indoor air quality, indoor environmental quality. And you might wonder, why is that so large? And the reason is that when you think about a commercial building, for example, the firm I used to work with, Environ, that 90% of its costs are its employees. Only about 10% are costs associated with the building, leasing the building, paying for the electricity, and so forth. So there does not have to be much benefit associated with things like decreased absenteeism, increased productivity, for that to translate to a very large relative number here compared to the others. But the important thing I want to point out is that the energy savings alone exceed the increased cost of building to LEED specifications. So if we do build to more green standards for our newer buildings, and we renovate buildings so that they're more energy efficient, then what is the low-hanging fruit? Meaning, where is the greatest benefit per dollar invested? McKinsey and Company looked at this question when it came to global expenditures to meet various levels of CO2 in the atmosphere. Here's 550, 450, and 400. And produced curves that look like this. And I called it low-hanging fruit because to me it kind of looks like a sorry tree, but a tree. Maybe some of the trees that the winds left for us over the past few days. And this low-hanging fruit here are all the things where the cost of abatement is negative, meaning the benefits exceed the cost. Because this axis is the cost minus the benefits. And so everything that is above the line, meaning everything here, it costs more than the benefits, assuming no benefits, of course, to decrease global warming. All of the things here, the benefits exceed the costs. And so what are the things here? Well, the big one here is building insulation, fuel efficiency of commercial vehicles, lighting systems, water heating, fuel efficiency in vehicles. That's one a little bit out of the topic. Sugarcane biofuel, and standby losses, and industrial non-CO2. So all of these, or most of these, are building related, suggesting that the benefits are likely to exceed the costs if we retrofit buildings to add more insulation, make them more airtight, and so forth. Now, how do buildings lose and misuse energy? First is air leakage. This means what it sounds like. You open the door and air rushes in and rushes out. You get a loss of energy or a gain of heat, a loss of heat in the winter or a gain of heat in the summer if you're air conditioning. Air leakage occurs around windows, it occurs around doors, it occurs at places in the building, on the sill plate and elsewhere where things don't come together very well or there's no barrier to air transfer or air leakage. Secondly, we have, and this of course is heat being transported by the transport of air, so-called convective losses. The conductive losses are those losses of energy or heat associated with heat transfer through walls and through windows, through doors. And then finally, inefficiency in the use of electricity, oil, and gas for heating and cooling. The type of system that we use, whether we have a very efficient gas condensing boiler that might get 90, 92, 93% efficient, or we have an old one that may be 79, 80% efficient. 2 years ago, a course here in the department here at Princeton called EPICS, Engineering Projects in Community Service, did air tightness testing of 39, actually 40 houses, including mine out in Hopewell, but they're reporting 39 here because they wanted to keep it all within the Princeton community. And they measured what is called air changes per hour. This is how much of the volume of air in a residence is exchanged every hour. And you measure this with a blower door. You just take the front door off, you put another door on it that has a big fan on it, and you either depressurize the house or you pressurize the house. And through a series of measurements, you can determine how much air is exchanged, how leaky the house is. If there's a window open, obviously you get a lot of air changes per hour. And what is obvious here is that the air changes per hour vary over quite a range, really a twofold range among the 40 houses that were, or 39 houses that were tested in Princeton. There seemed to be only a few houses that were down in this range, which are fairly tight houses. The Trade Association ASHRAE would suggest that residential houses not have air changes per hour less than 0.35 to maintain good air quality in the house. And houses that are designed to be very airtight often have mechanical ventilators called heat recovery ventilators. And these are mechanical ventilators that exchange the indoor air with the outside air, but in the process recover the heat that ordinarily would be lost. I don't believe any of these houses have such a device. I could be wrong. My house does have such a device. And I tried very hard to get my house very, very tight, but my builder wouldn't cooperate very well with me. And so my air changes per hour were about 0.4. I was striving for something much less than that, but 3 houses in Princeton beat mine. But you can see that the air changes per hour varied all the way, ranged all the way up to over 2. That means that every hour or every half hour, all the air in the house is being exchanged with the outside. mean, that's a lot of air changes per hour. And with that exchange goes the heat in the summer and increases with the heat in the winter, and then increases the heat in the summer if air conditioning is being used. So this is what one of the greatest benefits of an energy audit and with weatherization is to tighten up houses. Some of the houses that we looked at in Trenton, in fact, bore out the national data. These are data taken from the Energy Information Agency, and they are the energy intensity or energy consumption in thousands of BTUs per square foot. Now, we'll be talking about BTUs a little bit later on too. A BTU is a measure of energy. It's the amount of energy it takes to raise the temperature of water, 1 pound of water by 1 degree Fahrenheit. If you have which I do, a little 5-watt nightlight, an LED nightlight, the most efficient little nightlight you can get, that 5 watts would be using about 17 BTUs per hour, just to give you a sense of what a BTU is. And often we measure the energy use in a house by adding up all the energy, the heating, cooling, and so forth, and divide by the square footage of the house, and that'll give us an energy utilization intensity, EUI. And so one thing we notice here in these national data in the Mid-Atlantic region, that and this was of several thousand houses that were evaluated nationwide by the Department of Energy, that as the family income, the household income increases, the amount of energy used per square foot of house decreases, which you might guess would be true, that for low-income residents in the, say, less than $10,000 a year family income to say $25,000 a year or so, low-income residents in Trenton, the amount of energy used per square foot is quite a bit higher than it is in houses in Princeton and in the suburbs. Low-income houses is a special problem because many of them are lived in by tenants where they have no incentive to put money into the house. The landlord has no incentive because the landlord is not paying the utility bills. There are public programs, state programs, federal programs to provide assistance to low-income residents for weatherization, for energy audits and weatherization. ILS has a program to assist and to do such audits and weatherization. And what we have found in places where I've seen the data, including the few places in Trenton where we have some data, and particularly in places like Philadelphia where we have quite a bit of data, that the public assistance programs that provide energy audits and weatherization for low-income families result in about an improved energy efficiency of about 25 to 30%, which is very comforting because that would be our target for one of Pacala and Sokolo's wedges. This is not spending very much money, maybe a couple $1,000, $2,000 to $3,000 for an increased efficiency of 25 to 30%. Let's go on to commercial buildings, but before we do, I think we should review and just compare how energy is used in commercial buildings versus residential buildings. This is a little bit hard. You have to look a little close to figure this out. The yellow, or I'm not sure what color you're seeing, but the the lighter one, the lighter color is residential, and the darker is commercial. I see blue and green. I'm not sure what everybody else is seeing back there. And if you look across here, let's just look at the residential for a second. The residential, the big bars here are space heating and water heating. So if one compares among the alternative uses of energy in residential buildings, the two big uses of energy are space heating and water heating. And this would be true of us around here. If we look at commercial buildings, we see that the big bar here is not space heating, nor is it cooling, but it's lighting. And if you look at commercial space heating here and space cooling, and if you can tell where those line up here, about 17% and I don't know what that is, about a little less than 15%. You add those up, and you see that lighting in commercial buildings uses about as much energy as heating and cooling together, combined. Now, does that make sense? Intuitively, is that what you think is true of commercial buildings? We certainly know that commercial buildings, if we think about it, uses a lot more light, a lot more energy for lighting than we do in our residential houses. You go into most office buildings, and a room like this would be uniformly lit, or an area like this would be uniformly lit. We could just as easily read over in the corner there as back here at our chair or at a desk somewhere. Whereas in residential, we tend to task light. We use light where we're, in fact, we have light where we're using it. If we want to read, we have a chair and we have a light that allows us to read it at that location. We're not uniformly lighting our entire living room. So that's an important difference between the two. This is just simply pulling out the commercial piece to look at that pie, lighting 28% and space cooling and space heating together adding up to pretty close to what lighting is. And that's why you probably hear the term daylighting applied to commercial buildings. All buildings that would be built to be energy efficient, to be LEED certified buildings, would most likely use what is called daylighting. And what that means is the building would be designed or renovated in such a way to maximize the natural light coming into the workspaces with sensors that automatically dim the artificial lighting depending on how much natural light is coming in. So it's an optimum use of the lighting in the building, the energy used for lighting in the building by capitalizing on the lighting that is coming from the sun. This building, as an example, you can see has louvers and ways of getting light, the sunlight into the building. It's not easy to tell here, but the ceiling is sloped from outside to inside to increase the amount of light penetration into the interior of the building. If necessary to prevent glare, then you would use these curtains that there's some of them here in this building that would reduce the amount of direct sunlight on the workstations, and very efficient lighting fixtures, ones that have much lower, what's called much lower power densities than normal fixtures might have. The class that I have been engaged in for the last 2 years have had, as I mentioned, 2 projects. This is the Witherspoon, 190 Witherspoon Street. This is the warehouse building that Bob Hillier is renovating into his offices. And these are two adjacent buildings that will be downstairs. Commercial will be retail. This is the dry cleaner. And he will be developing two apartments upstairs in both of these buildings. This building is relatively small. It's about 6,300 square feet. And one of the first things that we did is we developed an energy model using a Department of Energy energy model for buildings, developed for buildings, so that we could determine what the beneficial impacts were of different things that you could design into this renovation. Things such as daylighting that I just mentioned, and this SRR is the skylight to roof ratio. This building has the benefit of being just one story, which means that you can put skylights on the roof to maximize the amount of light or optimize the amount of light penetrating into the working areas of the office building. And so we determined what the optimum skylight to roof ratio would be. And the reason there's an optimum is that the more skylights you have, because skylights typically are energy inefficient when it comes to conductive losses. Glass and windows usually don't have very high insulation, and so the more glass you have on the roof, the more losses you get during the heating and cooling season. So there becomes a trade-off between light coming in for use in lighting the building and losses of heat or gain of heat in the summer. And so if you look down through here, glazing is the type of glass. You can optimize the glazing depending on whether it's north, south, east, or west side of the building. Wall insulation, roof insulation. This is the heating and cooling system. This is photovoltaic panels on the roof, and in this case on what are called clear stories. And Mr. Hillier originally designed two long clear stories. These are like little mini houses on top of the roof that have vertical glass in them that allow light in, and they have a little sloping roof, and he's going to put PV on just those. And then we also evaluated what if we put photovoltaic panels on the entire roof. And we evaluated this incrementally. That is, this would be 0 is the percent decrease from the base run. So the base run would be a building that just meets code. And in this case, the ASHRAE 2004 code, which is the building code in New Jersey. And so if we improve the daylighting, if we use daylighting, the code doesn't require that you use daylighting, but if we use daylighting, meaning we enhance the amount of light we get in and we have automatic sensors that dim the artificial lighting, then this is the improvement we can get in the energy efficiency compared to the base run, which is just meeting code. And we have three bars here: annual energy cost, the EUI, which I mentioned before, the energy utilization intensity, BTUs per square foot per year, and we have the annual CO2 emissions associated with the energy use in the building. And you notice that these bars are not the same, that you get proportionately greater savings in annual CO2 emissions than you do for daylighting than you do in the EUI or the annual energy cost. And that simply means that in this building you're using electricity and natural gas, and those prices are different. And depending on how you reduce energy, whether you primarily reduce electricity and not so much natural gas because there are price differences, and there are also significant differences in carbon dioxide emissions associated with using electricity versus natural gas. And that's why you get these differences in these three terms. But the point is, you can see that as you incrementally add daylighting, more efficient windows, greater wall insulation, greater roof insulation, a more efficient heating and cooling system, and put photovoltaics either on these clear stories or on the entire roof, then you begin improving or decreasing the energy use in the building from code requirements, all the way up to, in the case of PV on the clearer stories, to greater than 50%. And if we put photovoltaic panels on the entire roof, we could actually decrease the energy consumption, total energy consumption of the building by 100%. And in the case of annual CO2 emissions, Mr. Hilliard could bank his CO2 emissions, and then when there becomes a tax or it becomes valuable sometime, he can sell it to somebody else. So that's the design that he chose, PV on the clear stories, and that together with these other features would reduce the annual energy cost by 68%, 50% reduction in the energy utilization intensity, BTUs per square foot per year, and an 82% reduction in CO2 emissions compared to what he is required to do by code. He also wants a green roof on this building. And so a good question is, what benefits does a green roof have? And there are many. But on the other hand, there is competition between a green roof and other beneficial aspects of things that can go onto a roof, such as collecting rainwater from a roof, which is the highest quality storm runoff that you can get from a site typically. But collection of rainwater from the roof and use inside the building or use as irrigation. If you have a green roof, then the green roof is absorbing some of that rainwater and evapotranspiring that rainwater. So it's taking rainwater away from the water that ordinarily or otherwise would be available for collection and use inside the building instead of the city water. Photovoltaic panels, most would say that there's a competition there. If you have photovoltaic panels up here, they would shade the plants. Although you can simply plant plants that like shade, and so it need not be incompatible to have photovoltaic panels. They obviously would have to be on a support at an angle to accommodate the plants. But the great benefits of a green roof, first and probably foremost, is it dramatically increases the life of the roof, maybe doubling the life of the roof. The roof of a building can get extremely hot, temperatures up to 170, 180 degrees in the summertime. And a green roof will reduce the temperature of the roof membrane down below 100 degrees Fahrenheit, usually. So increasing the life of the roof. And obviously it does decrease the so-called heat island effect. That is the effect in urban areas of all the impermeable and non-vegetative surfaces by increasing the amount of solar energy reaching these surfaces, in this case the roof. And in cities like Chicago, there is concerted effort to put green roofs as many places as possible, in large part for that reason. So we evaluated that in this building. We looked at the trade-off between the green roof and photovoltaic, and also the amount of water that was taken away from collecting and being able to be used inside the building. Turns out that the benefits of collecting roof water, even if there is no green roof at all, for a building that size, it does not have favorable benefits. That is, the present value costs exceed the benefits in this particular analysis of the 6,300 square foot building. We also, because Mr. Hillier very much wanted a geothermal system, a heating and cooling system, we evaluated a geothermal heat pump, or a ground source heat pump, or a ground coupled heat pump. They go by several names. And what that is it's a either vertical wells. A ground coupled system would be either vertical wells or horizontal trenches, where water is, or some solution is being circulated through the ground, and the ground is being used as a heat exchanger, much the way that air would be used to extract heat from with an air-to-air heat pump that many of us have, boxes outside with the fans on them. There are other systems. There are groundwater systems. There are where you pump groundwater through the heat pump and then back into the ground, or where you pump groundwater out and then into a local stream or a lake. There's also surface water, where you're exchanging the heat with a pond or a lake, or you're taking pond water in through the heat pump and discharging it somewhere else in the pond. Unfortunately, Mr. Hillier's property is so confined that it probably is not possible to put a geothermal system there. There's just simply not enough space. It's possible to have a groundwater system, but more testing would be required. However, at the Isles building, this is an old 1890s building that Isles is calling now Mill 1, we did design a geothermal, a vertical closed-loop system, because there was plenty of space both on this side of the building, the Amtrak line runs right through here, and on the other side. And indeed, that's what they're going to be building there, is a geothermal system. That would increase or reduce the annual energy costs for heating and cooling by about somewhere between 30 and 50%. And typically, a ground source heat pump can reduce the total life cycle costs compared to any other heating and cooling system. And finally, at the Isles building, there are 3 sections that we could put photovoltaic panels on, so-called A and A1, but together with the ground source heat pump and natural ventilation, we can achieve, we believe, carbon neutrality, meaning that the energy used that is the emissions, carbon dioxide emissions associated with the energy used, would be offset by the energy that is produced on site. So a question is, can we design buildings? And a lot of effort now is actually going into this, designing buildings to have zero energy. And there's a recent article in the trade press where the authors evaluated this for commercial buildings in 1999. They simply took all the commercial building data that they could find in the DOE database and determined the EUIs for those commercial buildings. And those buildings were about 84,000 BTUs per square foot. And developed a model, an energy model, that would allow them to test various changes that, if they were applied to these buildings, and evaluate what it meant in terms of energy reduction. And if all the buildings in 1999 were built to the ASHRAE standards, this is just what is required now, the 2004 building codes, the EUI would be 50, or a 41% reduction from the buildings that existed in 1999, which means that, assuming that these buildings were designed to code and were performing as such, that the increased requirements on energy efficiency in building codes that have occurred from 1999 to 2004 would result, if the 2004 standards were met, in a 41% reduction in energy use. And then if we add PV, they said, to half of the roofs of these buildings, then that would result, this is a little bit misleading because the energy used would still be generally the same, but what they're doing is they're taking the energy use here and subtracting from it the amount of energy that would be supplied by the photovoltaic panels. And that would result in another reduction, 28% reduction, from 50 to 36 kilobTUs per square foot. In other words, this building stock in 1999, if brought up to 2004 code, and if only half the roofs had photovoltaic panels, the energy use of those buildings for all purposes would be reduced from 84 to 36 kilobTUs per square foot. Then they went a step further and said, what if we do things that we normally would do in a green or a LEED certified building, such as elongate the building along the east-west axis. We provide daylighting, which I've discussed. We have overhangs to block the sun in the summer. We have lighting power densities. The fixtures would be much more efficient by about 17% than code, which is perfectly feasible. And we'd have modest improvement in the heating and cooling system. And the result would be a building that had, this would be the baseline if, in fact, these buildings met the 2004 code. This would be with half the roof PV. This would be the building with these LEED features, these energy efficient features. And these government scientists got together and said, what can we logically expect technology improvements to result in over the next 10, 15, 20 years? I guess this was 2005, the next 20 years. And there we see that we're actually negative, meaning that we're producing more energy than consuming through the primarily through photovoltaic and renewable energy sources. So zero energy buildings are clearly feasible. They're being built now for residences, the so-called passive house developed in Germany. I just heard last week a presentation of such a house in Illinois that is producing more energy than it is using. This is a building, a very energy efficient building at Oberlin College, the so-called Lewis Center. And that building is, has an energy use that includes photovoltaic panels 79% below code. And you can just look down this list at some other buildings around the country to get a feeling for how much more energy efficient these buildings are than would be required by building codes. The Science House in St. Paul, Minnesota is a very small, fairly small building, only 1,370 square feet. It has 8 kilowatts of peak power in photovoltaic panels. and it uses maximally uses the solar gain through passive solar design, and it is producing 37% more energy than it's using. How important is it to keep score, finally? Is it good enough just to design energy efficient buildings? Do they perform efficiently after they're designed and after they're lived in? Well, the answer is not entirely a good answer to that. There hasn't been a lot of studies, but there's been a recent one by the U.S. Green Building Council of LEED certified buildings, over 500 of them, and this is sort of the distribution of when those buildings were constructed, more and more as time goes on. And the energy utilization, the EUI, is of all these buildings where there was data and information on performance over at least 1 year of operation. And out of the 500 or so buildings, they could only get operational information on about 121 of those 500 and some LEED buildings. And out of the 121, only about 100 were typical office buildings. About 21 were high energy buildings, such as laboratories, which use a lot more energy than a normal commercial building would. And you can see the energy utilization intensity is spread out over a very large range. And of course, you can be a LEED certified building, and even more so a few years ago than now, and not be particularly energy efficient. There are a lot of other amenities that will get you LEED certification. But those buildings really are scattered over a fairly long, wide range of somewhere in the neighborhood of 20 up to about 140. And the average building in the Commercial Building Energy Consumption Survey of the Department of Energy was about 91. So you can see most of the LEED buildings are, in fact, better than that. But if we look at the design, that is, what was a building designed to do in terms of its EUI, energy utilization intensity, and what would it actually perform, we see that there's quite a bit of scatter there, that we have many, many buildings here that were designed for energy utilization, but the actual energy utilization was considerably higher than what was designed for, and just the opposite, quite a few buildings that perform better than their design. And finally, if we look at it another way here, we see that many of the buildings not only did not meet their design specifications in terms of energy use, but were even less than code required, which is particularly troubling. This is a LEED building that's not even performing up to code specifications. So we don't know what all of that means, but I think it underscores that we can't just simply renovate or design new buildings to be energy efficient without following their performance over time to be sure they're in fact performing the way they're supposed to be. In conclusion, making buildings more energy efficient makes good economic sense, security sense, and environmental sense. Better air tightness and insulation and improved efficiency in lighting, heating and cooling results in the greatest benefits. And finally, as I just said, it's important to monitor the performance of buildings over time to be sure that, in fact, they're functioning the way they are supposed to. So let me stop here, and I'm not sure what the timing here is. Do you normally go for, how much time do we have for? Please, I know some of you probably have even more experience than I do in this arena, so if anything I said doesn't make sense or you have something to add, yes, sir. Yes. Yes.
But I think that also over that period of time, we've gone from manufacturing everything to importing components from China.
Right.
So kind of outsourcing the energy and then claiming an increase in energy efficiency.
So we're cheating then to get that efficiency. But you would agree that, and maybe you don't know, but certainly manufacturing in this country is, over time, has been more efficient than it was back before the 1970s. Appliances have been more efficient and so forth. Yes?
A more simplistic question, perhaps. In the beginning, you mentioned that lighting was one of the big uses of energy.
Yes, in commercial buildings. Right.
So with all this new now lighting, 15 watts produces 60 watts, etc. Is that an actual reality?
The compact fluorescent bulbs, as an example? Yes. I think many of us are observing that the longevity of these bulbs is not what they're purported to be. Everybody agree to that? I've just lost, I bought all new bulbs maybe 2 years ago, and I've lost probably 10% of them so far. The new most efficient bulbs are LED, light emitting diodes, but now they're very expensive comparatively. But yes, they do significantly reduce, and at least if you believe the manufacturer in terms of longevity, the payback is a couple years.
And then as a follow-up to this lighting, again, as user of energy, if you drive, let's say down 287 at 12 o'clock at night, almost every office building that you see is totally lit up.
Right, because
Those people working.
the janitorial services are working at night. That's one of the main reasons why you see that.
Are they working on every floor?
No, I agree with you. I'm not making an excuse, but I mean there is some lighting at night because the janitorial services are in there. But I come into my office. I still do part-time work with Environ down at the Carnegie Center, and I was just there Saturday. I got in probably at 9 o'clock Saturday morning. All the lights were on, and I thought, well, is there anyone else dumb enough to be working on Saturday morning? And I concluded no. So I flipped the lights off, and they never came on the whole time I was there. So that suggests to me nobody else was in the building. But our office is a good example. All the lights for the entire floor of this building in the Carnegie Center operate by one switch. It's not zoned. If I come in and I'm just working in this area of the building, I can't switch just those lights on. I have to switch the lights on for the entire floor. And we're billed on a pro rata basis for the electricity. And we have 4 or 5 other tenants in that same building. So if we install efficient lighting fixtures or occupancy switches, which I failed to mention, but that turn the lights on when you come in the room, which is important to do, then we reap part of that benefit, but it's spread out. The benefit is spread out over the other tenants because we pay on a per square foot basis. So there are all sorts of disincentives for being energy efficient in existing office buildings. I could go on about our building. It's very inefficient. Other? Thank you. Building. I could go.